So I'm going to tell you about Twistronics, a new platform for exploring physics and applications in 2 dimensions. And I'll try to give a fairly broad, high-level presentation without too much detail, but I hope there's enough there also for the experts to be interesting. So I'll tell you a little bit about why we are interested in this, how we do some of the calculations, a little bit of physics background, and some of the methods that we have developed, and then what exactly we have discovered in this context, some neat physics, and lots of open questions still. First, a little bit about why 2D. There's very rich physics in 2 dimensions, and in particular, the 2-dimensional electron gas has been a subject of study for many decades, and it has revealed a lot of really beautiful phenomena. Here's just one representative picture. This is the fractional quantized Hall effect, having to do with Landau levels of the electrons, these orbits that the electrons undergo when they are confined in 2 dimensions and subject to an external magnetic field. And there's several Nobel Prizes here, starting with von Klinsing and Tsui, Stormer, and Laughlin. But there's also other important contributors to the field are Gossard and my colleague at Harvard, Bert Halperin. Bert, in particular, was the one who pointed out the importance and the beautiful physics of edge states in these systems, shown by these orbits here, which bounce around the edges. There's something down here hiding the bottom corner. There's a picture of Duncan Haldane there, who proposed the quantum anomalous Hall effect, which has to do with very interesting behavior in the absence of an external magnetic field, but due to internal effects, field effects in the system. However, in order to produce such a system, the 2-dimensional electron gas, this was a very difficult proposal. And it was realized after a lot of really hard work by experimentalists who perfected this kind of materials arrangement where you had different types of semiconductors, like aluminum gallium arsenide and gallium arsenide intrinsic. And in between these layers of very pure semiconductors, there was a tiny region where the electrons were confined. This was the confining potential produced by these materials. So the presence of these materials produced this effective potential where electronic wave functions in this direction were confined, producing this 2-dimensional electron gas. This took literally decades of perfecting the materials properties and so on. And it was a big development. But in the last few years, we have been blessed with a cornucopia of truly 2-dimensional materials. And those are semiconductors. Some of them are shown here, like transition metal dichalcogenides and hexagonal boron nitride and so on, and phosphorus, layered phosphorus, and there's also insulators, different types of insulators, and of course graphene, which is a metal. It's a semi-metal, but lightly doped, it becomes one of the best metals. And of course, this was another Nobel Prize for the discovery of graphene to Geim and Novoselov. And it produced a tremendous amount of interest and new exciting physics. So this is a more realistic version of graphene. There are ripples when it's not sandwiched between other flat layers. And of course, a very interesting aspect of all this is now that we have all these types of layered materials, how can we combine them? This is a standard picture from a paper by Geim and Grigorieva. Everybody more or less shows this picture in similar talks, so I felt obliged to do the same. However, it is a bit misleading because this depiction of the different layers as Lego blocks, which fit exactly on top of each other, is not really what happens in realistic systems. So different materials don't exactly stack on top of each other perfectly like Lego blocks do. And in fact, it's this mismatch, this dysregistry that has a lot of interesting implications and produces a lot of interesting physics itself. In fact, even if we put two or more layers of the same material, which in principle should stack perfectly, but slightly offset the perfect stacking, that's the twistronics, what they call twistronics version, then again, a lot of very interesting behavior emerges. Now, in order to have real applications, you need different types of components, and we do have those very well developed types of components. So you need a metal with zero band gap. I told you about graphene or layer, single or few layered graphene. You need semiconductors of various band gaps, and here's a very important family of semiconductors called transition metal dichalcogenides. There's different compositions, different number of layers. This allows you to play with the band gap. And there's also an excellent insulator, hexagonal boron nitride, with a very large band gap. And indeed, people have been already producing several types of devices. Here's an early example of this. This is molybdenum disulfide, one of these semiconductors. You shine light, you produce carriers, you excite carriers. Those can be transported away by the metal, graphene, and the whole thing is an insulating environment. So this is a very interesting arrangement for faster data communications from the group of Frank Coppens. Here's another example of real devices. And again, here's the semiconductor here, molybdenum disulfide, the purple with contacts with graphene. So graphene is the source and the drain on the semiconductor, and you sandwich these between different arrangements. You form these kinds of different gates, NAND gates, and so on, and you can make real devices. So this is from the group of Tomas Palacios at MIT. Indeed, it is expected that these types of devices will make very significant contributions to the reduction of energy consumption in Internet of Things devices, because naturally, being confined in the ultimate atomic thin layers, they have the lowest possible consumption in energy. A new game that appeared a few years ago, roughly 5 or 6 years ago, was the idea of taking two of these layers, putting them on top of each other, and twisting by a small amount. This creates a different length scale, much, much larger than the atomic length scale of the underlying atomic lattices. And in fact, in many situations, in most situations, it is not a truly periodic system. The periodicity is only approximate. If you look closely, this region here does not coincide exactly with this region here, only approximately for an arbitrary twist. There's special twist angles where there is periodicity, but those are very specific. And the length scale is adjustable by the twist, which gives a very interesting knob for considering many different possibilities. Okay, so just a couple of words of how this is done, because it really is quite extraordinary how this is done experimentally. So what happens is you put down one layer of the material, then you tear half of it by attaching another layer on top. And then you raise this half farther away from the other half, from the bottom half. But because they come from the same original layer, you know exactly their relative orientation. So you can twist the top half with respect to the bottom half in an arbitrary, by an arbitrary twist angle, and put it down again, and you have this twisted bilayer or multi-layer. So this is called tear and stack. And it enables what actually my colleagues tell me is control of the twist angle to 1,000th of a degree these days. This is an older slide. So many groups have applied this. This is an example from the work of Pablo Jarillo Herrero and Philip Kim, with whom we've been closely collaborating for many years. And this is the kind of picture that you produce by dark field imaging with scanning, transmission, electron microscopy of these types of layers. Very interesting patterns. The patterns are different if you do different materials. What I showed you a moment ago was graphene. This is molybdenum disulfide on molybdenum disulfide, and you can stack those in two different ways. At 0 degree or 180 degree would be the perfect stacking. So this is half a degree off one stacking. This is half a degree off the other stacking, 179.5 degrees, and you produce different patterns. Now, the calculations that we try to do to understand and explore these types of situations are based on realistic representation of the degrees of freedom, of the electronic degrees of freedom. And this is all done within the context of density functional theory, the so-called Hohenberg-Kohn-Sham approach. Theorem that enabled this. This is a picture of Walter Kohn, one of the developers of this theory, who actually was also acknowledged with a Nobel Prize for his contribution. So you end up solving these equations for the single particle states. And there's an important aspect here is the presence of the ions, a realistic external potential for the electrons. And there's also a contribution that is approximated, but without having to go back to experimental input. So this is all within theoretical considerations, the so-called exchange correlation potential from exact calculations of the electron gas. So it does involve this kind of approximation, but it nevertheless is a totally ab initio type of approach. It allows us to calculate the total energy and atomic forces and have a realistic representation of the structure of the system. And therefore, it allows predictions which can explain and guide experiment. Its limitations are that it can only handle of order a few hundred to 1,000 atoms on a regular basis. And it assumes a crystal structure, an underlying crystal structure. So now going to graphene, the physics of graphene is basically determined by the honeycomb lattice where the atoms are situated. There's 2 atoms per unit cell, and in each atom we think of attaching this kind of PZ orbital. It's actually a little bit more complicated than that. I'll show you in a minute. And this is what produces the energy of the states near the Fermi level being proportional to the momentum. And these are the linear dispersions right here, shown here in 2 dimensions in kx and ky space, which are the so-called Dirac cones. Shaded region here are occupied states, unshaded is empty. This is the Fermi level, and this is where the linear behavior is, right very close to the Fermi level. One important aspect of this is that graphene, as I mentioned already, is a semi-metal in the sense that right at the Fermi level, the density of states is 0. There are no states at the Fermi level, but slightly above and below there are. And in fact, it was suggested early on that if you could hit these regions up here or down here, where there's large densities of states referred to as Van Hove singularities or flat bands, so then you might even be able to make graphene into a superconductor. But of course, accessing these layers up here or down here is very, very difficult because they are several electron volts away from the Fermi level, from the intrinsic, the charge neutrality point. And because of that, this was deemed impossible. And basically what the twist of the 2 layers does is it allows us to create large densities of states very close to the Fermi level, to the neutrality point. In terms of the actual structure of the system, what happens when you have one layer on top of another, you create these regions where the stacking of the two layers is, for instance, in this region called the AA region, the top layer shown in orange atoms completely hides the atoms of the bottom layer. In other regions called BA or AB, those are related by rotational symmetry or translational displacement. So the top layer, again in orange, hides only half of the atoms of the bottom layer. And in fact, the low energy structure, the structure that the system would prefer is exactly this one. And this is a high energy structure which the system tries to avoid. But because of the twist, you have both of them, as well as regions that separate those two, shown here by the blue lines, which are called the domain walls. So when you have this twist in real space, you also have a twist in reciprocal space. So the Brillouin zone in the reciprocal space that I showed a moment ago for a single graphene layer, now you have two of those, the red one and the blue one. The large-scale periodicity creates this supercell of the Brillouin zone, which has, which is the small black hexagon, and the corners of that black hexagon come from half of them from one large hexagon, the blue one, the other half from the red large hexagon, and these are the corners where the Dirac cones appear. That's what you have from each individual layer that I showed you a moment ago, but now you have two sets of these in the supercell Brillouin zone. Now, a key contribution in understanding a lot of these, a lot of the physics associated with this came from this seminal paper by Bistreitzer and MacDonald in 2011, who pointed out this simplified but quite powerful pictured how to think about these systems. So here's the supercell Brillouin zone that I showed you again with a blue graphene Dirac cone in one corner and a red Dirac cone in the other corner. So these are shown as dashed lines here, and of course they intersect. The distance between the centers of these cones is dictated by the Moiré length scale, by the twist angle. So the smaller the angle, the closer these two cones are. Where the cones intersect, of course, this degeneracy will split, and the amount of splitting has to do with the interaction between the layers. So there's two different energy scales here. Importantly, when you have this splitting here, you produce bands that are flatter than the original bands, and the Fermi velocity here, the slope of the states is also renormalized, and this leads to this kind of density of states where you have these two lobes associated with each one of these bands, and density of states here is significantly higher than in graphene. Just to give you a sense of the comparison, the single graphene density of states, as shown here schematically by the dashed lines, in order to make it visible on the same scale for the density of states, has to be multiplied by roughly a factor of 1,000. So this is significantly enhanced relative to the density of states of the single graphene plane. Now, there's a lot of really interesting other implications of this simple picture, and I want to point out some of them because what I'll show you later is in contradiction to this. So it goes beyond this simple picture and makes significant changes the perspective significantly. So here's here are some of the predictions of the continuum, so-called chiral model by Bistreitzer and MacDonald, and these are some of the band structures that they produced. At different twist angles, 5 degrees, 1.05 degrees, and 0.5 degrees. And here are the so-called flat bands, which produce the very high density of states. and especially at 1.05 degrees, you see these very prominent flat bands. So the flat bands are related to these so-called magic angles. This quantity here is the renormalized velocity, the slope of the bands at the Fermi level, as a function of this parameter alpha square. Alpha is inversely proportional to the twist angle. So as we go along in this axis to higher values, you go to smaller and smaller twist angles. So this very first point where the velocity becomes zero corresponds to approximately this 1.05 degrees of twist. But you see that there are several other points, several so-called magic angles, where the velocity vanishes, specifically 1.05, 0.5, 0.35, 0.24, and 0.2 degrees along this axis. So these are some of the predictions of this simplified model. Now, as I mentioned already, the layers are incommensurate for an arbitrary twist angle. So there's a question of how to describe the system. And we have been fortunate to work very closely with a group of wonderful mathematicians. Their names are listed here: Paul Cazot, Mitch Luskin, and Daniel Massa. And they helped formulate this kind of picture where you describe the system in terms of configuration space. And the idea here is that if you look at these two layers in real space, the blue and the red dots representing the two layers, and blow up some of the local environments, you realize that there's a range of local environments, local displacements of the top layer relative to the bottom layer. And you can describe all these local environments by considering one layer to be the origin and shifting the other layer relative to it in all the possible ways. So this kind of shift produces all the possible local environments that can be produced. And in terms of the local environments described by this little variable, by the variable little omega, you can then have integrals over all this space of local environments called capital omega. And these integrals of any function that depends on this local environment can give you the observables. This is the analogy that we draw with the integrals over K space, which is what we typically use for systems that have perfect periodic order. And it's the average over K space of different quantities that correspond to the physical observables. But of course, in order to have this possibility to describe the system in terms of local environments, you would need a Hamiltonian that has finite range. And we worked quite hard to produce such a Hamiltonian. I don't want to go into a lot of details here, just to give you a sense of what's involved. So this is called Vanier states, and you can do this using these wonderful tools that David Vanderbilt and Nicola Marzari and collaborators have developed. So you can construct by unitary transformation localized states in space that give the same physics as the extended states in periodic systems. So this is what we find for the localized states in graphene. You do have the contribution of the pz orbital as expected, but also you have higher angular momenta. These are important and useful in reproducing the exact same results as the extended states. So you attach these kind of a little bit more complicated orbitals to each site, then you figure out the interaction between them from ab initio calculations, and then you have a very accurate description in terms of interlayer coupling of these localized orbitals, and you can do quite realistic calculations. So that's what we did in this paper. Back in 2017. So this is now the density of states on the vertical axis. On this axis is the twist angle, and on this axis is the energy. And at zero twist angle, you get this plot of density of states for graphene that I showed you already, with zero density of states at the Fermi level. But at around 1 degree of twist, you start developing a large density of states, and this depends on the twist angle. which is what allows you to do interesting explorations of the physics of the system, because now you can indeed dope the system lightly and have carriers, depending on the twist angle here, different density of states, and this gives rise to interesting behavior, as I mentioned. So that's what we call the twistronics, the ability to adjust the behavior of the system through the twist angle. And in fact, I told my student, let's put this term on the in the title of the paper. This was a Phys B paper, and back in the days when I was a student and we were trying to publish papers in Physical Review B or letters with fancy words, even in the abstract, the editor would immediately remove that. Nowadays, I guess even Physical Review is getting a little bit more lenient, and they accepted that, and then a little, yeah. That's right. That's right. And then some of the popular press picked that up. Physics World here, Twistronics tunes 2D materials properties, and Wired magazine, the coming age of Twistronics. So that was quite fun to see that. But one key aspect of the system is that the density of states in real space, where the electrons are in real space, has very interesting behavior as well. So this is what I showed you earlier in terms of AA, AB, and BA types of stackings shown here at the bottom. And the high density of states in real space, where the electrons are localized, are in the AA regions, in the regions which are of high stacking energy. So this is important for further discussion. I'll come back to it. And of course, localized electronic states correspond to flat bands. However, if you look at the overall pattern, which looks like this when you put one layer on top of another, the blue and the gray dots here, this looks nothing like the experimental measurements. So this is graphene, this is molybdenum disulfide. So you see kind of a mess here with no well-defined regions, at least of the type that is in experiment. So where does this come from? Well, this comes from atomic relaxation. And then the effects of atomic relaxation, I believe, are very important and need to be taken into consideration in order to have a realistic description of the system. So this is a structure of the system before allowing for atomic relaxation. This is what happens after you allow for atomic relaxation. Atomic relaxation here in this particular study from the group of Elad Tadmor is taken into consideration by using an interatomic potential, an effective interaction between the atoms that tells you the energy of different atomic configurations. And this is at a rotation of 2.13 degrees. You do see, without relaxation, AA regions, AB regions, and the boundaries between them. But upon relaxation, the AA regions, which are the high energy stackings, shrink very significantly. The AB or BA regions, which are equivalent, increase in size very significantly. And of course, you can't avoid the boundaries between them. And interestingly enough, the relaxation also introduces an additional local twist. So this is a local twist of the AA regions beyond the overall twist imposed on the macroscopically on the two layers. So you can think of the system as something like this. There are the AA regions here, which shrink and twist more than the overall twist angle that you are imposing. And interestingly enough, the large green triangles representing the AB or BA regions twist in an opposite direction by a smaller amount, which depends on the length scale of the pattern. So this is a very interesting type of situation. And yes,
a quick question.
Please, yeah, please.
Is the lattice mode which produces this localization, is it really essentially entirely a spatial variation of twist, or is there a dilatation in and out also?
It's mostly a twist because graphene is very stiff, so there's not much change in bond lengths. And basically, this kind of twist allows the system to take up a lot of the strain that you would have if you simply expanded or contracted these regions. And this twist essentially accommodates this strain by the twist of the small regions, the counter twist of the large triangles, and the shift of these regions. So these are kind of slightly shifted relative to each other. Yes.
I'm sorry,
Yeah, I'm not sure if I. Yeah.
Then is the energy for this essentially a lattice energy, meaning that this relaxation would happen regardless of the band filling of the flat bands? Or is it driven by electrons, so it's biggest when the flat bands are half filled?
No, this is independent of the flat bands. In fact, I'm going to argue the reverse. It's this that produces the flat bands, which are separated from the rest. I'll try to explain that a little bit more. Yes. So this is driven by energy of the lattice, independent of the bands, but it has a big effect on the bands. I'll show you, and I hope this will be more clear. Yeah, so this is a little bit trying to, again, in that direction, try to motivate why this is happening. It's similar to the physics of dislocations, not exactly, but in analogous in a broad sense. So in a dislocation in a crystal, you have an extra plane of atoms on the upper half relative to the bottom half. But of course, the system does not relax by matching all these layers and expelling this kind of defect all the way to the edge. It relaxes by this slight deformation around the dislocation, and this is exactly what this relaxation does. So this is what is called a dislocation, there's another reason why I'm bringing this into the picture. So the energy of this dislocation is described in terms of elastic energy for the slight deformations, and the misfit energy. This is the atomistic contribution of changing the positions of the atoms in the neighborhood of the dislocation. This is called the Piles-Nabarro equation, and it allows you to minimize the energy and produce a profile for the dislocation. That is the profile, namely the small displacement of the atoms around this defect, and this is the density of the dislocation, essentially the derivative of this. The way to calculate this extra contributions, the so-called misfit energy, was first proposed by Jim Rice. This is a seminal paper by Jim Rice, who came up with this idea of the generalized stacking fold energy. So this is the idea that if you cut the crystal into halves, the perfect crystal, and you slide one half, the top half with respect to the bottom half in all the possible ways, for a single unit cell, periodic unit cell, you generate an energy landscape. That's the generalized stacking fold energy. This energy landscape is what produces this misfit energy. So that was Jim's very important contribution. And I'm going to rely on this concept in the following slides also to justify what we are doing. So you have the total energy as the interplane energy and the intraplane energy. This can be calculated relatively easily because it's essentially due to linear elasticity. The stretching of the atoms within the plane is well described by linear elasticity because the deviations are very small. It's a stiff material, very small deviations. So the interplane energy now is, we model this through exactly the generalized stacking fold energy, as I described earlier. And this depends on these vectors, the little b vectors that I mentioned earlier. Those are the configuration space vectors that I described a few slides ago. And we add this local deformation u, so that's what the capital B vector is. And then we integrate over all possible local environments, and that's what gives us the energy functional. And using now this idea, here's a few pictures of the generalized stacking fold energy for graphene. Those are the two planes of graphene, sliding them on top of each other for a primitive unit cell, just a 2-atom unit cell per layer. You don't have to go to large unit cells. So this is what generates these generalized stacking fold energies. The dark lines are cuts through this. So that's the cut through the graphene generalized stacking fold energy. I have here two more examples for molybdenum disulfide with cuts through these energies and so on. Just to show you that this is a general concept, we can apply it to any material. And then introducing the local deformation U and allowing and optimizing the energy, minimizing the energy. This is the landscape that we produce. And this is in configuration space, and we can translate this back to real space, which produces now these relaxed atomic configurations. So here are the large triangles, here are the small circular regions or hexagonal regions, and here are the domain boundaries, all produced by this relaxation mechanism. And it is these large triangles that correspond very nicely to the patterns that are observed experimentally, and these large hexagons, which are correspond again nicely to the patterns that are observed in a different material, molybdenum disulfide, because its generalized stacking fold energy is very different than graphene's generalized stacking fold energy. So this is for an ideal crystal or two ideal stacked layers with relaxation and so on. In experiment, you always have some degree of defects or intrinsic strain, which makes the pattern not quite perfect, but you can clearly see this hexagonal pattern rather than the triangular one in graphene. Okay. And we have spent a lot of effort trying to make sure that what we are seeing really corresponds to experiment. These are experimental results from Philip Kim's group, and this is a work that we published a few years ago, looking at the diffraction patterns with the details of each spot in the diffraction and how those are very accurately predicted by the atomic structure that we find through this relaxation. So there's a very nice correspondence there. There's another very interesting thing, which I'm showing you here for, again, 3 cases, graphene, molybdenum disulfide in these 2 arrangements, 0 degree or 180 degree and twists relative to this. So let's just concentrate on graphene, and the others are similar. Going down the list here of figures, the angle of twist becomes smaller and smaller, starting at 2 degrees, 1 degree, and so on. And this is the configuration space, these panels, and this is the translation to real space. So if you look at what happens in configuration space and then you go to real space, you realize that right about 1 degree of twist, you see 1 degree of twist, you see the clear formation of the red small regions. The black regions will start to be triangular and the boundaries between them in white. If you go to smaller angles, the pattern does not change. Only the length scale changes. The pattern is exactly the same, and the size of the black triangles increases. Everything else remains exactly the same, which is really quite spectacular. It tells you that right at 1 degree, which is the magic angle that we mentioned earlier, the pattern sets in, this relaxation pattern that I was mentioning, and then it doesn't change from then on. Okay. Now, so here's another view of this pattern. So this shows you also the relaxation in the vertical axis, which is significant. The distance between regions of AB or BA is 3.35 angstroms, the vertical distance. That's almost exactly the same as in graphite, where you have an infinite number of planes in their ideal stacking, whereas the distance between AA regions is about 3.6 angstroms. So this is about 10%. This is a significant relaxation. It's sort of enhanced here to show it, but on the atomic scale, it's quite significant. And as I was mentioning earlier, it does have an important effect on the electronic structure, coming back to Andy's question. So this is the electronic structure with the full relaxation. And here are the flat bands near the Fermi level that produce the high density of states. This is the band structure without the relaxation. And this is basically what the Bistritzer-McDonald model predicts. Here are flat bands again, but very strongly hybridized with all the other bands and no band gaps anywhere. So this is a crucial thing, because in experiment, we do see band gaps, as I'll show you in a moment. And again, coming back now to compare with the predictions of the simple qualitative model. So this is the Bistritzer model besides the McDonald model again. This is the curve that I showed you earlier with multiple zeros here, multiple magic angles. Here is our calculation without relaxation. Of course, we can take the atoms and just freeze them in the positions without relaxation and do the calculation. And it looks quite similar. Here's our result with full relaxation. Indeed, you get these flat bands with zero Fermi velocity. This is the unique magic angle at 1.1 degrees approximately, but there's no other magic angle. Okay, this is a complicated plot. I'm going to try to describe it in words. Basically, this shows you that there are three important features of the flat bands. One is the width of the bands. The other is the slope here at the edges, the Fermi velocity. And the third is the gap between the flat bands and the other bands. And in this picture, we basically say that the width in blue, the gap in red, and the slope in dashed black, all these features are optimized near the magic angle, around 1 degree. Not in a unique value, but in a small range of roughly 0.1 degrees around this. And if you think about it a little bit, it has to be this way, because if it were a unique angle, experiment would never hit it. Because in experiment, there's always some variation, defects, internal strain, and so on. Whereas if there is a small range where all these features are optimized, as I just explained, it is possible to observe it experimentally in many different situations. So this is what we think is happening, and I hope this gives a better description in relation to Andy's earlier question. Yes, please.
Yeah, I have a question on this plot of the Fermi velocity. So what is the difference between the green and the red lines? So are those obtained from the continuum?
Yes, the green line is the Bistreiser-McDonald model. I just copied exactly their curve. Okay, that's the curve from their paper, just copied. This is what we get if we freeze the atoms and do not allow them to relax. We put one layer on top of the other with frozen atoms. That's what I call unrelaxed. And then we allow the atoms to relax, as I was describing, to find their optimal structure, which forms this nice pattern of triangles, domain walls, and the small AA regions. And that's what produces the bottom line.
So the red line is obtained by the
it's our calculation.
DFT calculation?
Yes, exactly. Yes, yes. It's based on the model that I was describing, right? Yeah, correct. Yes, it's all within our framework for doing calculations of this, including these, realistic Vanier functions and so on, but with frozen atoms. So this looks very close to this model, which makes sense because this is an underlying assumption of this simplified picture. There's no information about the relaxation in the simplified picture. Okay.
Could I ask another question?
Yes, please.
So usually one thinks of forces in terms of like a Hellman-Feynman theorem, where you know some electronic ground state and then ask what the forces are. I mean, here you're kind of these there's forces coming from these very local calculations that are in a pretty different electronic ground state than the full system. Is there like a hierarchy of energy and length scales where maybe long-range electronic parts are now considered or approximated as lower in energy than the atomic relaxation, or what?
Yes, that is a good point. You're absolutely right. It does involve some level of approximation. So the energetics comes from this stacking fold energy that I was describing. Okay? But that describes the system in sort of a general way. It doesn't have all the details there. And it corresponds to a different electronic structure, you're saying. So we're assuming that landscape, energy landscape, even though it comes from these assumptions, is realistic enough to produce reasonable relaxation. At some point it fails, and I'll show you where it fails. This is a great point that you're raising. Yes, yes, this is a great question that you're raising. Okay. Now, of course, there was tremendous excitement in the community when these papers appeared by Pablo Jarillo Herrero's group. at MIT, and actually my student Xiang Fang and I were included in this work because my student was working closely with Pablo's students at that time and helped develop the thinking of how to approach the system. So they put these twisted bilayer graphene in this device, lowered the temperature, and found superconducting behavior shown schematically here. So resistance goes to zero. I should point out that the temperature, the TC is rather low, 1 degree Kelvin, but nevertheless, I think there's a way of thinking about this that justifies an approach that implies strongly correlated electrons. This is the picture that described some of the physics in the system in Pablo's work. Basically, you have this vertical axis is the conductance, which can be thought of as representing the density of states in the system. The horizontal axis is the carrier density, which can be thought of as representing the energy as you're moving the energy level up and down relative to the Fermi level or the charge neutrality point. So this is the Fermi level for a neutral system. So here you're doping with holes, here you're doping with electrons, and you would expect these nice domes here that I was describing earlier, separated by band gaps. Here's a large band gap separating the flat bands from the rest. Here's another band gap here separating the flat bands from the other conduction states, but there are also additional smaller gaps here splitting these density of states. Now, if you blow up this region here around this range of doping, and you plot the carrier density, the temperature for the transition as a function of the carrier density is a phase diagram. Now you have these superconducting regions and separated by mode insulator regions and so on. And this has certain very important similarities to the phase diagrams of high temperature superconductor for the cuprate materials. Notice here that this is for 1.16 degrees. This is for 1.05 degrees, again, superconducting regions, mode insulator, and so on. And you see, as I was describing earlier, a range of values where this happens, consistent with the kinds of things that I was describing. Of course, the presence of these mini gaps cannot be explained within single particle theory. So here's single particle theory, the bands that I've been discussing. And in this picture, full band occupation separated from the rest by a gap is described by this picture. Half band occupation means basically that all the K values up to the Fermi level correspond to field states. So in real space, you would have half an electron up and half an electron down per site in half filled band, but certainly no gap. So you have to go to this kind of mode insulator description where you have one electron of spin up or down in each site distributed in a way that so there's no net spin. If you go beyond single occupancy per state, you pay an energy of U. So that's the Hubbard model here, where each side is occupied by one electron. Double occupancy costs U in energy, and there's a hopping energy of T for moving between sites. And of course, you need to go beyond the filling of this half lobe, half band lobe, so to speak, by doping with electrons or holes to produce a state where you can have free carriers. In the case of cuprates, the lattice is relatively simple with simple atomic orbitals on each side, either oxygen-related atomic orbitals or copper-related atomic orbitals. So we can think of the system in this simple picture. As I was describing in some detail earlier, here we have A, B, BA, and AA regions, all of them large on the atomic scale as well as at domain walls, this picture that I showed you. And this is a much more complicated situation. If you look at all the AA sites, they form a triangular lattice. If you look at all the domain walls, they form a Kagome lattice. And if you look at all the triangular large region triangular sites, they form a hexagonal honeycomb lattice. So it's really much more complicated. If you were to try to do a simple description with all these superimposed lattices, it would be really a mess. We try to figure out what exactly is happening by analyzing the character of these flat states. So here are the bands again. So these are the flat bands. They're never completely flat. They always have some level of dispersion. And here's their analysis in different, their projections in different wave functions. So the orange wave functions correspond to states that are localized in the AA regions of PZ character or PX plus or minus IPY character. These are the contributions of the wall-related states, and these are the contributions of the AB or BA states. This is the multiplicity of each one of them. If you sum them all up, you have 10 states here per unit cell, per moire unit cell. It's really rather difficult to reduce that to the simple model that I was describing earlier, so you can think of Hubbard physics. Moreover, yes?
I mean, I thought that the two flat bands were 8, basically. So where's the other 2?
Well, okay, I'll show you another model. So this is by trying to understand all the contributions here. So there's 3 here, one of S character and 2 more of PX plus IPY character. There's 3 centered at the walls, and there's 2 in each of the triangular states, A, B, and BA. So that's 10. But that's not a unique model. So this is another version of this. We try to do an even more thorough investigation. So you start with trial wave functions, localized wave functions. You pass them through the model with chiral symmetry to impose the right symmetry. Then you compare them to ab initio band structures, and you fix the parameters to reproduce these bands. And this is how we ended up with either 8 bands or 5 bands. So the 8 bands are the 2 flat plus 3 below and 3 above. Or the 5 ones are the flat bands and only the 3 below or only the 3 above. So that's kind of the minimal model that you can construct using these Vanier type of arguments, trying to localize the states, but they're still not localized. They extend over several unit cells in the neighborhood. And here are some of the wave functions.
But just to make sure I understand
yes.
what you mean, I mean, if I just count bands,
Yes.
right?
Mm-hmm.
Do I have it right that the flat bands, which are shown in blue here, really, if I include, so if I leave out spin, there are 4 flat bands.
Correct.
Which are degenerate.
Yes.
So your statement is that if I have 5 or 8, because here we're not counting spin, if you have 5 or 8, I take basically those 4 states plus some fractional overlap to these other bands, and then there are also yet other bands which aren't included in this Vanier description, which are sort of in the same range.
Not quite. I'm only showing the bands from one valley. So I'm not showing 4 bands. So there's the valley degeneracy. So the K and K prime, the 2 different Dirac cones. So here I'm only showing one set of bands. So there's a degeneracy because of this. So there's 2 more of them. Okay. So let's forget that complication and concentrate on this. So even those, I cannot only consider those 2. What I'm trying to say is that you can't just isolate those 2. You need the other 3 above and 3 below.
But yeah, I guess, but my only trivial question was, it looks like there's more than 3 above and more than 3 below. So is the statement that if I just look at the band structure and project it onto these Vanier functions, some of the extra above and below bands, which are shown in the band plot are not included in these Fourier functions.
Yes.
Or is this the statement that yeah, oh, okay. All right, thanks.
Does that make sense?
Yeah, no, that makes perfect sense. I
Okay.
don't know what Fourierization is. I'm just trying to count the bands and relate the number of bands to the number of Fourier functions that are being included.
Yes.
But I think I sort of have the picture of what you're saying now.
Okay. Because yeah, if I try to describe the flat bands, there's always some weight beyond those two. Yes. And that's why I need the rest. That's the idea. Okay, now, I don't have much time left. Okay, by the way, I would like to emphasize that, in my opinion, this is still an open question. It's not clear that that's the end of the story. By the way, the Vanier states that I'm showing here are consistent with what I showed you earlier. Most of the wave functions are localized at the AA region, so it's consistent with this picture that I showed you, which is also consistent with what experiment like STM experiments have showed us. I don't have a picture to describe this now. So I have quite a bit more slides to show you, but I don't have time. So what I'm going to do is I'm going to flash very quickly through them just to sort of give you an overall view of many other things that are going on. So I showed you the picture of the bilayer. Of course, you can have more than 2 layers. You can have 3 layers, 3 Dirac cones, again, flat bands, but also more complicated situation. You have 2 twist angles. The cell size goes as 1/θ². Theta is the twist angle. And of course, you have 2 independent twist angles. The reason for looking at those is because experimentally they have been realized. So here's a picture for tri-layer graphene with superconducting domes. Interestingly enough, the superconducting temperature is 3.4 Kelvin, quite a bit higher. And we have been working hard on this. You can extend the same configuration space picture to these tri-layer systems, and my student Zoe Zhu has done a wonderful job in analyzing the patterns here, the relaxation patterns, which involve similar twists as the ones that I was telling you earlier, but it also involves the formation of larger and larger moiré length scales. So this is basically a moiré of a moiré of a moiré if you keep zooming out. Quite complicated. You need 3 Brillouin zones, and you can construct this kind of effective Hamiltonian. You have many more scattering possibilities that satisfy the conservation of momentum. So the scattering selection rules, and that's what produces a lot of very interesting features in the band structure. Here's a band structure for a particular set of twist angles, large density of states at the Fermi level again, but no gaps anymore. You don't find gaps anywhere. And we can extend also this. Very recently, we published again a paper on phonons. You can construct a moiré Hamiltonian for the phonon degrees of freedom. The diagonal are from individual layers. The off diagonal are the interlayer interaction terms. The same kind of situation, and you can produce phonon bands for different twist angles using this idea. So this is the work of Zoe and an undergraduate student working in my group, Jonathan Liu. And here you see some interesting features like breathing modes, which at large twist angles are very flat, then they change quite a bit. And shearing modes, those are the red ones highlighted here. And some of them have negative frequencies. That's where the model fails. Okay? And you can't get rid of that no matter how hard you work because of this imperfection. You don't get all the details perfect. And there's interesting patterns of the atomic displacements. So this is 1 degree twist, layer 1 and layer 2 atomic displacements, 7.34 degree twist, again, layer 1 and layer 2. And these are top views, and you see these kind of rotational atomic displacements corresponding to the breathing modes between the layers that I was highlighting. Here's another set of issues that we've been working hard on. This is an idea that I'm quite fond of. This is the idea of Janus transition metal dichalcogenide bilayers. This work started with my student Roderick Quaid-Defoe. And the idea is that I showed you a few pictures of transition metal dichalcogenides. These have a metal layer in the middle and chalcogen atoms on either side. And our idea was to take the middle layer of metal atoms and put different chalcogen atoms on the two sides. And the experiments realized this a few years after we predicted it. Interestingly, we called it mixed layers. They called it Janus layers. So that's a lesson. Always invent a fancy term. And now everybody refers to this paper and calls them Janus layers, although we actually predicted them and described the physics quite nicely. The interesting thing here is that you can play a lot more games because you have different stacking possibilities, many more interesting regions here, relaxations, AA regions, XM, MX, domain was AB, XX, and so on, depending on how you stack them, how you put them on top of each other, and the different overall arrangements called 3R and 2H. And this is work that my postdoc, Mattia Angeli, has done. The interesting point is that you can describe all the physics by a single band continuum model, where all of the parameters are essentially derived from ab initio calculations. And the overall potential that appears in these single band structures, again, depends strongly on relaxation, before and after relaxation, but it can have very different overall patterns. For example, you can create an overall triangular effective lattice, or a honeycomb effective lattice, or a Kagome effective lattice for the electrons in these single band models, and play with these states, and you have flat bands again, and so on. So there's a wide range of possibilities here, and I think that's quite exciting. And we've also worked on automating the kind of calculations that I was presenting to you for many layers. So here's examples for 5 layers with different numbers of layers twisted, different possible ways. You even need a language to describe all this. We've invented a language to model this, to identify this. And we've worked quite a bit with doping these layers with additional atoms, inserting different types of atoms here, which possibly could be captured by the overall relaxation pattern to make for interesting possibilities, such as trapped ions that might serve as localized qubits, and so on. So I don't want to go much longer. I just want to give credit to a lot of people who contributed to this. I already had pictures of my students who did most of this work. So Shang Fang, Stephen Carr, Zoe Zhu, and Roderick Quaid-Defoe, they're all postdocs now. Shang is at MIT, Stephen is at Brown, Zoe is at Stanford, and Roderick is at Princeton, and they're in the job market. And if you have positions, hire them. They're all wonderful. And a lot of postdocs also contributed to this. And we had the great fortune to work closely with many experimental groups. I mentioned already Philip Kim and Pablo Jarillo Herrero and several other colleagues at Harvard and beyond. The group of mathematicians with whom we work closely to produce some of the framework that I described, and with other theory colleagues, Ashwin and his students, and Subir and his students, and so on. So I'll stop here, and these are the different foundations that supported the work, and thank you for your attention, and take any additional questions. Thank you.
Thank you, Jim, for the action-packed, really illuminating talk. Questions?
Yeah, coming back to my original question. So you showed beautifully that this reconstruction and let's say compression of the AA regions was driven by lattice effects. So one may then ask the next question, which is, how strongly does it couple to electrons? In other words, if I were to change the band filling of the black bands from empty to half filled, how much would this distortion change?
Yes, that's a good question, but I believe the effect will not be very large. The reason is the following. If you look at the density of states associated with these bands, the number of electrons associated with these bands is minuscule, is really tiny. The overall unit, the Moiré unit cell is huge, is of the order of tens of thousands of atoms. And the number of electrons associated with these bands are just a few electrons in tens of thousands of electronic states. So I think changing the occupation of these bands is not going to affect the overall structure.
Yeah.
Does that make sense?
Oh, that makes perfect sense. I was thinking about it from the other point of view to ask how strong is that? Does that give you an electron phonon coupling to the electrons in the Moiré bands?
Yes, yes, that's a very good point. And in fact, I think there's a lot to be done there. In fact, we are doing very careful calculations, trying to do as good a job as we can, again, from the ab initio point of view, to quantify electron phonon coupling. I think it's going to be very strong. Precisely because of this, I didn't have time to describe it in more detail. Several of the phonon modes are exactly localized, and they have this kind of rotational twist kind of character, exactly localized where these states are. So I would expect that there's indications here that we're very strong electron phonon coupling. I'm not sure if that will really drive the many body character of the system, but it's really worth exploring, and hopefully we'll have results for this soon. Yeah, absolutely, very good point.
So experiment have seen that so TBG in particular, correlated states in TBG are somehow, in some cases they are present, in other cases they are not present, and it seems that it's also important the role of the substrate. So
Yes. Yes.
TBG is suspended on HBM, and whether the substrate is aligned or not.
Yes.
Yes. So do you think that you can have a, let's say, if you include the effect of HBM in your relaxation,
Yes.
do you believe that there are effects on the flat bands?
Yes.
And
Yeah.
What are these effects?
Yes, that's a very good point also. So in my view, the HBN, at least from what I've seen so far, the effect of HBN is not very important in the flat bands themselves. And the reason is that these effects are important where there's some kind of overall periodicity, so to speak, and pattern forming, so the states are strongly affected, the electronic states are strongly affected. HBN differs in lattice constants from graphene, and the alignment is not usually perfect. So essentially, this leads to an average potential from HBN on the graphene layers. And it's this average potential that essentially washes out, doesn't strongly affect these states. That's the sort of picture that I have in my mind. Unless you take care to very carefully arrange the two layers so that there's an overall pattern that emerges and affects these states, I don't think it's a big effect. And I think the only significant effect is to make the graphene layers very flat themselves, because otherwise, no, they tend to have ripples. Now that graphene by itself, especially suspended, it always has ripples.